Hello, I am Alberto Tufaili and I'm going to present Magneto-Optical effects, Einstein ring, and ferrofluids. And the authors are myself and Adriana P.B. Tufaili. We are from Software Matter Lab, University of São Paulo, Brazil. The main idea here is to study the formation of hyperbolic lanes using a thin film of ferrofluid subjected to a magnetic field in a device known as Ferrocell. This device has interesting effects when interacting with light, such as polarization and unidirectional light scattering. In this work, we present a comparison between the patterns obtained with this device and Einstein rings obtained with a hyperbolic lens formed by a pseudosphere based on geometrical theory of diffraction and hyperbolic geometry. Well, this work is a sequel of these two works, Halo Dynamics from Rainbows to Black Holes, presented at this conference in 2020, and Horocycles of Light in a Ferrocell. If you want to learn more about the Ferrocell, we wrote this book. It's open access. You can find this book at the web. And basically, Ferrocell is a thin film of ferrofluid between two glass plates subjected to a magnetic field interacting with light. And you will have some patterns like this. Basically, when light interacts with the ferrocell, it scatters light in some directions. So why? Because the magnetic field creates some structures inside the ferrofluid due to the formation of the columns of nanoparticles. When light interacts with these structures, they are oriented by the magnetic field, and light is scattered in some directions like this. Well, this is a diagram of the demonstration that we will present now. You have the observer, the ferrocell, a magnet close to the ferrocell in order to produce the magnetic field, and the light source. So here you can see this animation. This animation was done by Doug Hatley. Again, when the viewer changed its position, it observed these light patterns like this and changed his angle of observation changes the pattern observed. This is the experiment, and you can see the phenomena here. You have the source of light again. Let me show you again. You have the source of light, the magnet, and the light pattern. In between the observer and the light source, you have the ferrocell. Besides this experiment using Ferrocell, we compare the system with gravitational lensing. Uh, if you consider the Einstein's gravity field equations, this famous equation, some of the solutions of these equations are related to gravitational lensing. So you have the source of light here and the observer here in Earth. And when light propagates through the space, in the presence of massive objects, you have this lens effect distorting light rays. Demonstration for a gravitational lens, it can be seen here. One possible solution of these equations is the sealed sphere lens, because they can be broken into simpler equations, the Einstein field equations, which are more appropriate to understand the gravitational lensing, considering the case of the lens with the shape of a foot of a wine glass for a point mass model. The angle which light is deflected by this point mass is given by this equation, and this is the sealed sphere. So, changing the angle of the observation, a point turns into these arcs, and let me show you this effect here. So you have this point, and changing the position of the observer, you have this formation of these rings. Now we are coming back for the starting point. So this is an image from NASA for this of this gravitational lensing. And one thing that's interesting in these two pictures is that you can observe the explosion of a star, a supernova. You can see the supernova here. This is the supernova and the star in this place, and these two images are the distorted images from the original one. You do not have three galaxies and stars. And this picture was taken in 2016, and here in 2019, it disappeared this star. There is a prediction that we will see again in 2037. This star will appear again in 2037. This is another image of the other gravitational lens. Well, here we have the hyperbolic glass. We learned this subject from this paper, Hyperbolic Geometrical Optics, Hyperbolic Glass, from these authors. It's well known that geometrical optics approximation of the wave equations is related to the asymptotic form of the integral representation of the field, which is an exact solution of wave problem. And they consider in this paper that the ray trajectories are the lines orthogonal to the constant phase surface and are described by the Acknowledgment equations. So the light rays are geodesics of the light wave. And they associated this problem with the geometric theory of diffraction of Joseph Keller. So in this problem of gravitational lensing, you have an object emitting light here and a telescope here, and you can see this light is being bent. The ray of light are bent by the presence of this galaxy cluster. And they consider in this paper that the light rays are geodesic of Euclidean space, phase and amplitude of this light wave are real valued functions, so you can measure it, and they are related to Fermat's principle, in which a path is one that requires the less time. And they obtained this horocyclic flow in a Poincare disk for this system. What is a horocycle? A horocycle can be described as the limit of the circles that share a tangent in a given point as the radii go towards infinite. So this blue circle here is the horocycle. And for the case of the gravitational lens, they observe these horocycles. And one important thing that they used here, that instead of use the Fermat principle, they are using the Jacobi principle, in which, in other words, they place in this way. In place of Fermat's principle, which reads this integral, where dt is the travel time measure, and p0 and p1 are prescribed starting and end points of the path. We write this integral here, and they have some propositions for this problem, and they have this proposition of hyperbolic waves related to horocyclic waves and conical functions. Well, observing our system, returning to our system of ferrofluids in the Ferrocell, we have the formation of these horocycles when we change the position of the observer. We have some initially a point. After that, we have the circle, and this other, we change it again, the position, we have this another circle, and they are enlarging and becomes a parabol and hyperbola. And for this case here, we can see the same system. We put a magnet in this position here that we called monopolar configuration, and we have a strip of LEDs, LEDs, where we can see the formation of these horocycles. So for different angles of observation, we have the larger circles. And for the case of dipolar configuration of the magnetic field, we also have this deformation of these ellipses and the formation of parabola and hyperbola. So we can see that there is some kind of conics present in this system in which we have a ferrofluid subjected to a magnetic field. This magnetic field creates columns of nanoparticles. We also call microneedles of nanoparticles. And these microneedles are aligned with the magnetic field and scatters the light in a direction perpendicular to the incident of the incident light. Just to have an idea of what is happening. If we consider that we put the monopolar configuration, when we place a pole of a magnet at the top of the ferrocell, these red lines are the magnetic field. These blue lines are the isopotentials, and the light patterns are these circles tangent to this point. For the case of a dipole, we have the magnetic field lines here. These green lines represent the isopotentials, and the black circles here represent the light patterns. So you can see that we have transformation of the magnetic field to these light patterns. There is a relation between casual relation between magnetic field and the light patterns. We could imagine that we have a conic, and the ferrofluid is crossing this conic in some points when you change your point of observation. You have circles, parabols, and so on. In this paper, good vibrations packing rules for diabolic points, we have this idea of conic sections and these tangent inner circles. Basically, this Horocycle model is based on this idea. The ray comes from the source, is spread perpendicularly to the magnetic field, which here behaves like a geodesic. We have the formation of luminous circles, the formation of horocycles. The fields, isopotentials, are circles. The Möbius transformation, we consider the Möbius transformation by inversion that leads from one circle, equipotential, isopotential, to another circle, horocycle, passing through the light source at the perimeter axis and the center of the magnet when we change the angle of sight. So in this way, we have basically this system. We have the magnet here, the field lines, the magnetic field lines, and the formation and the pattern formation here. So we can imagine a simplified version of the magnetic field here with this radial lines in these concentric circles of isopotentials. We have a transformation of the magnetic field to the light patterns, the magneto-optical patterns that we see in the ferrocell. And this transformation, this function f, is somehow related to Möbius transformations of circles into another circles. And this happens when you have a sphere, mapped in this way, and we have a transformation from this system of coordinates to a bipolar system of coordinates. So we have a transformation from the magnetic field by a function that creates the magnetic patterns in this system that is similar to the bipolar coordinates. And here you can see the transformation of this circle using Möbius transformation in this circle inside this region. So this is one circle is transformed by another circle by Möbius transformation. In the paper of the hyperbolic length, we have a mapping of a horocycle in the disk D into a Beltrami sealed sphere. And here you can see some images of the light horocycles in the Ferrocell system. Well, at this point, we present our conclusions that halo formation based on geometry theory of diffraction is found both in gravitational lens systems and in the formation of light patterns in ferrofluids. Both cases, relativistic and Ferrocell, show the formation of Horocycles. In this way, we have in both systems some kind of hyperbolic lens, both in the Ferrocell and the case for the relativistic system of gravitational lens. In this way, we have not the same system, but a similar system between the formation of image from the relativistic system and formation of light patterns from this magnetic optical pattern formed by the ferrocell, magnetic field, and a light source. These are some of our references, and this is the book that we suggested, and these are some papers that we published about the system, and a paper about the formation of halos, dynamics from rainbows to black holes, and we acknowledge to the Brazilian research agencies and Doug Hartley for the animation of the system showing the ferrocell. Thank you.